Hi everyone. In this video, we'll go through topic related to relations. We'll go through domain and range of a relation and go through different types of relations such as reflexive, symmetric, transitive, equivalence, and antisymmetric relation.
What is a relation? Say, for example, we have two sets A and B, right? And when you get the Cartesian product of these two sets, that is when you do A cross B, right? You get a list of ordered pairs, correct? Right? R is a subset of A cross B. That is, R will have ordered pairs, right? Which will be from this particular set itself. So if you take these two sets, say set A as BCD and set B as CDE, right? Now you can form a relation R. You can form a relation between these two sets A and B. So elements in this set is related to the elements in this particular set, right? Now that relationship can be anything. Here the relationship is given as next letter in English alphabet. So if B is the set, what is the next letter for B? It is C, right? So now you see there is a relationship between this and this. What is the relationship between B and C? C is the next letter in English alphabet for B, right? After B comes C. So C is the next letter for B. So there is a relationship between B and C. Similarly, if I take this element C, then what is the next letter for C? It is D, right? In the English alphabet, next letter for C is D. So you'll have C and D. Now C and D are related. C here and D here are related. How? D is the next letter for C. Similarly, if I take D, right? D from set A, right? How is it related to any element here? So what is the next element for D? It's E, right? So E is here in this set. D is in this set. So D and E are related. And what is the relationship? Next letter in English alphabet. So basically, if I take A into B, if I take the Cartesian product of these two sets, right, set A and set B, what will be the Cartesian product? What will be the list of ordered pairs? These are the list of ordered pairs I will get. B with C, B with D, B with E, B C, B D, B E, then C with all these three elements. So C C, C D, C E, then D with all these three elements. So D C, D D, D E. These are all the set of ordered pairs, right, in A into B. Now what is R? R will be another set. R is another set which has a relationship between set A and set B. And what should the relationship be? It should be next letter in English alphabet. So which are the pairs here which have next letters? B, C, right? This satisfies this relationship. If you take first element from set A and second element from set B, the relationship should be that this second element should be the next letter in English alphabet or first element. So you have BC. Is BD satisfying this particular relationship? No, because D is not the next letter to B. Is B satisfying? No. CC? No. Is CD satisfying? Yes, because D is the next letter to C. So this is satisfying. Similarly, CE? No. DC? No. DD? No. DE? Yes. E is the next letter to D. So this is satisfying. So now out of this entire A into B, there are three ordered pairs in R. Basically, these ordered pairs satisfy this relationship. So now if you notice, R is nothing but subset of A into B. Let's take another example. Say we have two sets P and Q. P is set of alphabets A, B, C. Q is set of names. Say Ali, Banu, Chandra. These are names. Now, what is P cross Q? That is, what is P into Q? You'll have put all the combinations. A with Ali, A with Banu, A with Chandra. Then B with Ali, B with Banu, B with Chandra. Then C with Ali, C with Banu, C with Chandra. So these are all the ordered pairs for P into Q. Now, I will define a relation R. Between X and Y. X and Y you consider X is the element from set P and Y is the element from set Q. That is, X is coming from here, Y is coming from here. X is the first element, Y is the second element. First element is coming from set P and second element is coming from set Q. The relationship is the first element, that is X is the first letter of name Y. So now how will I form the set? I'll take, say, first element from set P. Say I'll take A, right? I'll take this first element A. And then the second element should be from set Q and it should start from A because it is told that X is the first letter of name Y. X. Here, first element is A. A should be the first letter of name, Ali, Y. So A, Ali, B, Banu, C, Chandra. Basically, these are the ordered pairs that satisfy this relation. So look at the set again. Look at the set. This set is having so many ordered pairs. But which is the ordered pair that is satisfying this condition? A, first letter, Ali. Then you have B and B for Banu. C for Chandra. Right? Only these pairs are satisfying. So basically, relation is nothing but set of ordered pairs that satisfy a relationship between elements of one set with the elements of another set. And that relationship is denoted as R. Now, what is domain and range of a relation? Domain is nothing but collection of all first elements of ordered pairs in R. Right? We found R here. Say in this example, we have R defined here. All the first elements form the domain, and all the second elements, that is Ali, Banu, Chandra, they form the range. So all these elements are range, and all these first elements are domain. So ABC is in the domain, and Ali, Banu, Chandra is in range. So let's take an example. Say we have relation R with all these ordered pairs. Now what will be the domain for this? Domain would be first elements 1, 1, 1, 1, 1, 1. So we have only 1 here. What is a range? Range is a collection of all second elements 2, 3, 4, 5, 6, 7. So range is 2, 3, 4, 5, 6, 7. Let's take another example. Here relation is given x and y, right? X and y are related in such a way that y is x cube, right? This is the relation. Y is x cube, where x is a positive prime number less than 10. X is a positive prime number less than 10. So what are the positive prime numbers? Let's call that as set A, right? Set A is nothing but set of positive prime numbers. So 2 is a prime number, 3 is a prime number, 5, 7. These are the prime numbers which are less than 10. Positive prime numbers less than 10. This is set A. Now we have one set here. What is R? We'll have to derive R, right? R is equal to, it is having ordered pair. XY is the ordered pair, where X is a positive prime number and Y is equal to X cube, right? This is the relation. We'll have to pick X, and then what will be Y? Y will be X cube. So X and Y is the ordered pair. So if I take X, X is 2. Now what should be the second element? It should be Y, which is X cube. What is X cube? 2 cube, right? Similarly, we'll take second element 3. For 3, what is the second element? 3 cube, right? Y is equal to X cube, right? Then we'll take next element 5. 5 should be 5 cube. Then 7. 7 is 7 cube. So this is R. This is relation R, right? Now, this is nothing but 2, 8, 3, 27, 5, 125, 7, 343. So now, what is domain here? Right? We need to find domain and range. Domain is all the first elements is the domain. So 2, 3, 5 and 7. What is range? Range is all the second elements. This is the range. Nothing but 8, 27, 125 and 343. This is range. What is inverse relation? So if you have relation R between set A and set B, then relation inverse, that is inverse relation, denoted like this, right? Inverse relation is nothing but relation from B to A. Just reverse this. From B to A, it is inverse. So if R is having these ordered pairs, so these are the ordered pairs for R, then what is inverse relation? Inverse R, it will just be reverse all these numbers, reverse all these elements. So instead of 2, 8, it's going to be 8, 2. Instead of 3, 27, it's going to be 27, 3. Instead of 5, 125, it's going to be 125, 5. So this is inverse relation. Let's go through types of relations. There are multiple types of relations. Some of them are reflexive, symmetric, transitive, equivalence, identity, null, right? Let's go through reflexive relation first. What is a reflexive relation? A reflexive relation is nothing but for every element A that belongs to relation R, A comma A should also belong to R, right? You basically take this element and the ordered pair in R should have A comma A. So for example, take this set A is equal to 1, 2, 3. And R is defined like this. R is set of ordered pairs, right? Now I take an element from A, right? Say 1 I take. If I take 1 from set A, I should have 1, 1 in R. Then only it's called as reflexive. And this should happen for all the elements. So I should have 1, 1. Let's go to the second element 2, 2, 2, third element 3, 3. So I should have this kind of ordered pairs in relation in R. Only then I can call this R as reflexive relation. So here you have 1, 1, you have 2, 2, you have 3, 3. You can have other ordered pairs also. But to prove that this relation is reflexive, you should have same element in the ordered pair. That is, first element and second element should be same. The next type of relation is symmetric relation. Symmetric relation, here if you have an ordered pair A, B in R, then you should also have ordered pair B, A in R. Say this is set A with 1, 2, 3, 4, 5 elements. Then say you have R1. Some random relation have picked up R1. It has these ordered pair, right? 4 ordered pairs are there. Now here look at the ordered pair. 2, 3 is there, right? If I have 2, 3, then I should have 3, 2. The reverse also should be there in the same relation. If I take 3, 4, then 4, 3 also should be there, right? And all these elements, 2, 3, 3, 2, all these belong to this particular set, right? So if I take 2, 3, then the reverse combination 3, 2 should be available. Only then will I say that this relation is symmetric. So R1 is symmetric. Let's go through relation R2. R2, 1, 5, 5, 1 is there. 2, 5, 5, 2 is there. So this is also symmetric. Let's go to relation R3. R3. You have 2, 3 here. 3, 2 is there. So this is fine. You have 3, 4. So you should have 4, 3. 4, 3 is not there. So this is not symmetric relation. Let's go to R4. You have 1, 5. Do we have 5, 1? No. So this is not symmetric. The next type of relation is transitive relation. This states that if A and B and C are ordered pairs in R, then A and C also should be an ordered pair in R. That is, if I have 1, 2 and 2, 3 in R, right? If I have these two ordered pairs in R, then I should also have A, C. That is, this element and this element should be in R. That is, 1, 3 should be in R. If 1, 3 is in R, then I call such relation as transitive relation, right? Have to take the first element and the second element of the next ordered pair. A and C should be in R, should belong to R. Now, let's take this example. So, we have set A with 1, 2, 3, 4, 5 as elements, and this is relation R1. Let's take this first ordered pair. 1, 2 is there. 2, 3 is there. So, what should happen? I should get 1 and 3 also here. I have 1, 3, right? Now, let's go to the next one, 2, 3. 2, 3 is there. 3, 4 is there. So, what should happen? I should get 2, 4. 2, 4. So, I have 2, 4. So, this R1 is transitive. Let's take another example where it is told that set A is a set of natural numbers, right? Set A is a natural numbers. So, basically 1, 2, 3, 4 till infinity, right? There are infinite natural numbers. And R is a relation on set A. So, there is relation R on this particular set. And what is the relationship? E is a multiple of. This is the relationship. So, now let's take, for example, set A is 1, 2, 3, 4 till infinity. I'll say 16 is a multiple of 4. And say R will have 16, 4. 16, 4. What is the relationship between 16 and 4? 16 is a multiple of 4. That's what is told here, right? The relationship is E is a multiple of. So 16 is a multiple of 4, right? Now, next one is if 16 is a multiple of 4 and 4 is a multiple of 2. 4 is a multiple of 2. Then, if these two pairs are there in R, then by transitive relation, 16 should be a multiple of 2. That is, you're taking this one, and this one. You should have 16, 2. And if you observe, 16 is a multiple of 2. Hence, it satisfies the condition for transitive relationship. Here we took an example of multiple of 4. You can take any example, right? You can take any number, say multiple of 3, multiple of 5. Any example if you take, that is, if you take x is a multiple of y and y is a multiple of z, then z will surely be a multiple of x. So you can take any number and try this out. This condition will hold good. Equivalence relation. What is equivalence relation? A relation that is reflexive symmetric and transitive is called as an equivalence relation. Let's take an example. Say we have three straight lines, L1, L2, L3. Now, relation would be E is parallel. Every straight line is parallel to itself. We'll have to prove that it is reflexive, right? Reflexive means what? To itself. A comma A should belong to R. That is L1, in this case, L1 is parallel to itself, right? Every straight line is parallel to itself. So reflexive condition is met. Next one should be symmetric. What is the condition for symmetric? If AB belongs to R, then BA should be belonging to R. So if L1 is parallel to L2, can I say L2 is parallel to L1? Yes, right? If L1 is parallel to L2, L2 is parallel to L1. So it is symmetric. Instead of AB, it's L1 and L2. L2 and L1. So symmetric is satisfied. Let's go to transitive. What does transitive say? If A comma B belongs to R and B comma C belongs to R, then A comma C should belong to R. Only then we can call this as transitive. Now, instead of A, I have L1. Instead of B, I have L2. Instead of C, I have L3. If L1 is parallel to L2, that is A comma B. If L1 is parallel to L2 and B comma C, that is L2 is parallel to L3, can I say L1 is parallel to L3? Yes, right? If this and this is parallel, this and this is parallel, then this one and this one should be parallel, obviously, right? So L1 comma L3 is parallel. L1 is parallel to L3, right? That is A comma C. So therefore, it is transitive. Since this relation is reflexive, symmetric and transitive, this is called an equivalence relation. So next type of relation is antisymmetric relation. Antisymmetric relation states that if A and B belongs to R, BA belongs to R, then A is equal to B. Now how do you arrive at such kind of a relation? So there is one such relation called as E is less than or equal to. Less than or equal to. So if you have a set of integers say 1, 2, 3 till infinite. This is a set of integers. In this set of integers, can I have two numbers which are less than or equal to each other, right? Is there any two numbers that you can pick up where both are less than or equal to each other? Can 2 be less than 3 and 3 be less than 2? No, right? It's not possible. The only possibility is if I take the same number, that is 2, 2. Because in this case, 2 is less than or equal to 2 because 2 is equal to 2, right? Only in this case, this condition is satisfied. If you have a relation like this, where x is equal to y and this belongs to R, that is in this case, say for example 2, 2, and if this belongs to R, then such kind of a relation is called as antisymmetric relation. With this, we've come to the end of this particular topic. Thanks for watching. Hope this video was useful.